Okay, we're going to look at section 8.2, testing a population mean. So we're going to look at, we think there's a certain population mean, and we're going to see if that's actually correct, or if we think it might be different from that, based on the test results we have gotten. All right. So X is going to be the random variable we're going to look at. If we are drawing these from a normal distribution, a bell-shaped curve distribution, then any sample size is going to work, and we'll have to be told that in the problem. Otherwise, we should look for samples of at least 30. We're going to state the null hypothesis and an alternative hypothesis, and we're going to determine whether this is going to be a one or two-tailed test that we're working with. Again, when you're figuring out the null hypothesis, that's the one with the equals. This will equal the predicted value, and then the other one will be, whether we're looking for it just be different, or if it's greater than or less than, that'll be the alternative. And we're going to be given a level of significance here. How much do we want to think that are we willing to be wrong? That's what the level of significance is. How much error are we willing to allow to be wrong with this? We're going to find a test statistic and the corresponding p-value, and the p-value is what's the probability you would hit that value or more extreme. When we calculate the test statistic. If we know sigma, we're going to use z, and we're going to calculate this test statistic this way with our standard error underneath, or you can adjust the formula and look at like this. If you don't want to calculate the standard error by itself, you can use this version of the formula. If we don't know, then we're going to be using the t-values, and kind of the same idea, divide by the standard error. And again, you can manipulate the formula and change it so it looks like this. So again, pretty typical stuff with this. We're just calculating these test statistics. So nothing really new going on here. And again, the degrees of freedom, one less than the sample size when you're using the t-values. So nothing new there. Determine the results of the test based on the p-value. If your p-value is less than or equal to your alpha, your level of significance, then we're going to reject the null hypothesis. Okay, so the idea is like, let's say I say there's I want my alpha to be 5%. So what I'm willing to say is I'm willing to be wrong 5% of the time with this kind of testing. And so I get a p-value where it says this value you would only get it, 2% or, less than 2% of the time. And I say, well, I'm willing to be wrong 5% of the time. I don't think we're in the null hypothesis is true. I said I'm willing to make a 5% error. It's only 2% likely this would actually happen. That falls within that range. So that's what this comparison is talking about. If that p-value is greater than alpha, and it doesn't matter how much greater. If I say I set an alpha level at 5% or 0.05 and it comes out to be 0.051, I do not reject the null hypothesis. That's why we set it there. It's like, no matter what, you don't move the bar. You're just like, it's got to be 5% or lower, and if it's more than 5%, that's it. That's I'm not willing to go that far. For examples where sigma is known, we're going to go back to 8.1. So we're going to be looking at situations where we don't know sigma, the t-values. All right, so let's look at page 468, number 8, and I did a little snip here. So for a student's t distribution with degrees of freedom of 16 and a t-value of negative 1830, find an interval containing the corresponding p-value for a two-tailed test. So here's the two-tailed test, right? And we're going 16 degrees of freedom. So I kind of snipped the table here, 16 degrees of freedom. And we're going to try to find our value. Now, even though this is a negative, you always use the absolute value of that. The negative just means, you know, you have your curve, you're way over here, so you're looking at that value and lower. But because of the symmetry, that's exactly going to be the same as the absolute value or the positive version of that t value and higher. So that's how the kind of the table set up with positive values instead of negative values. So we're just going to use the absolute value of that. So I want to go in here, and so this is what they're asking me to do. Like, okay, I got 16 degrees of freedom, and I go through these different t values, and I come in here. This is where my t value should be. Remember the positive version, the absolute value version of that. It should be in there. Well, it's not on the chart. What am I going to do? Well, that's why it's saying find an interval. It's saying this is my interval. This is my p-value, the probability I would get that value or more extreme one way or the other, left, you know, left in the case of the negative value, right in the case of the positive value. The probability I would get something that extreme or more would be somewhere between 5 and 10%. So my interval is going to be, my p-value is going to be somewhere between 5 and 10%. Okay. Now, if it says you have an alpha value of 10%, then this would tell me to reject because my value is less than 10%. If it said I had an alpha value of 5%, I wouldn't reject the null hypothesis because this is more than 5%. So now if it said, what about a 7.5%? Well, I don't know. I don't know the exact value using this chart to figure that out, to make that determination, and you won't have to face that on the homework or the test. But you know, I know it falls in this range, and in fact, I know it's more than 5%, and I know it's less than 10% because it's neither of those numbers. So it's got to be somewhere in between there. Find an interval containing the corresponding p-value for a left tail test. So, you know, this is looking this way, left tail. Well, that's just going to match, again, symmetry of a right tail test. This is so the big deal is this is a one tail test. This is a one tail test, right? So now I'm going to look at the one tailed, and kind of the same idea, 16%, go to that value, but this time I'm looking at these two numbers. So for a two-tailed test, or sorry, for a one-tailed test, this value falls between 2.5% and 5%. Would be that or more extreme. So, you know, if this time it said 5%, well, yes, I would reject the null hypothesis. If it said 1%, no, I wouldn't, because I know it's more than 2.5% chance I would land there or more extreme. Okay, so that's how we're going to get those intervals. So when we're doing this, we're not going to get like, you know, the probability of me getting that value and lower is, you know, exactly 0.0256%. You know, I'm going to get an interval. It's going to usually be between two values of percents. And I'm just going to have to kind of say, okay, it's somewhere in there, and then use that to determine whether to reject the null hypothesis or not. All right, let's look at number 12. So on number 12, 464, and I think probably there was a lot more of this that I just didn't want to, you know, take up the entire slide to snip it here. So let X be a random variable that corresponds to the pH of arterial plasma or acidity of the blood. For healthy adults, the mean of this distribution is 7.4. So we got that. Gives a reference for that information. A new drug for arthritis has been developed. However, it is thought that this drug may change the blood pH level, the acidity of the blood. A random sample of 31 patients, so we got N equals 31, with our arthritis, took the drug for 3 months. Blood tests showed that the mean was 8.1, so looks higher, you know, on there, with a sample random standard deviation of 1.9. Use an alpha level of 5% to see if it has changed one way or the other. So let's do our hypothesis. Our null hypothesis would be that this mean is still 7.4 for these patients. And then our alternative would be that the mean is not 7.4. So this is going to be a two-tailed test. That's the either way is kind of keying you off on that, higher or lower. You know, it's just going to be different. So we're going to figure out our t value. And again, that's going to be, the formula for that is our mean minus our sample mean minus our predicted population mean over our standard error divided by the square root, or sorry, our standard deviation divided by the square root of n, or alternatively, we can use this version, which is the version I'm going to use here to calculate this. So 8.1 minus our predicted mean was 7.4, square root of our sample size, 31, and divide that by our sample standard deviation. And I don't have a calculator, just a second. Right. So let's do this calculation. Parenthesis 8.1 minus 7.4, close it up, square root of 31. Get out of the square root, divide by 1.9. And that gave me a t value of about 2.05. And it might help to kind of, you know, I'm looking at this t value, 2.05, and I'm going more extreme. That's how the table is going to tell me. So I'm going to look at my t value charts. And I also need my degrees of freedom. And hopefully I don't mess it up. If you watch one of the earlier videos, I messed up degrees of freedom. So that's going to be our sample size minus 1, so 30 degrees of freedom. So we're going to look at 30 degrees of freedom line and try to find what category for a two-tailed test would give us a t-value of 2.05. So 30 degrees of freedom and 2.05. So I have 2.042 and 2.457. So between those, that's where this value would fall. And for a two-tailed test, this would be between 2% and 5%. So 2% p-value and 5% p-value. Okay, so this is our level of significance. If the p-value is 5% or lower, we reject the null hypothesis. It is less than 5%. Reject the null hypothesis. So the claim the drug has changed the pH level, yes. Well, I shouldn't say that. I should say we can reject the null hypothesis, that it has stayed the same. That's what we would say. We would reject the null hypothesis. So yeah. All right. Let's look at this one. Number 14 here. Pyramid Lake is on this Indian reservation in Nevada. The lake is famous for cutthroat trout. Suppose a friend tells you that the average length of trout caught in the Pyramid Lake is 19 inches. Okay. However, the Creel survey reported that the random sample of 51 caught a mean of 18.5 inches, an estimated standard deviation of 3.2 inches. Do these data indicate that the average length of trout caught in Pyramid is less than the 19? Use an alpha. All right. So null hypothesis. I'm going to set up our hypotheses here. Null hypothesis is that, and again, sometimes it's easier to do the alternative versus the null. This one we're asking, is it less than 19? Is it less than, that means this is greater than or equal to 19, would be the null hypothesis, that it's that the average is still 19, or the average might actually be higher. We don't know. All we're trying to see is it less than 19. That's what we're really trying to determine. Okay, so do these data indicate? All right, so we need to find our t-value. So we're going to take our sample mean, 18.5, minus our predicted mean. We're going to multiply that by the square root of our sample size and divide that by our standard deviation. So 18.5 minus 19, square root of 51, divide by 3.2. And we get a negative 1.11. Okay, we'll say 1.116. So I think all the values in that chart have 3 decimal places. All right, so this is what we're really trying to figure out is from this value here and lower, is that going to be smaller than this alpha? But again, the table isn't really set up for that. It uses absolute values. So we're going to come over here to positive 1.116. And that's the value we're going to use on the table. I'm going to go that way. Again, symmetry, it doesn't matter. But it's good to understand what's going on when you're doing that. Why am I using the positive value versus the negative value? Well, because of the symmetry, I can do that. And that's how the table is set up. So degrees of freedom are 51 minus 1, so 50 degrees of freedom. So I go to my table, 50 degrees of freedom, looking for this positive 1.116. And oh, it's a good, oh, so I have 0.0679 and 0.116. So this would fall in between those. This is a one-tailed test. So I'm gonna go all the way up the table, and that tells me it's somewhere between 12.5% and 25%. That's where my p-value is. Well, that's clearly more than this alpha value. So do not reject the null hypothesis. Okay, don't reject the null hypothesis. We can't say it's actually smaller. Just because you got an average size from your sample of 18.5, it's just not different enough that we think the entire population average is probably off of there. Now, notice one thing we're not doing is we're not saying that the null hypothesis is true. That's not what we're saying. We're just saying we don't have enough evidence to say it's false, which are not the same thing. You know, it's like, well, if you're not saying it's true, you must be saying it's false. Or if you're not saying it's false, you must be saying no. We're just saying, based on the evidence we have right now, there's no reason for us to say it is false. But that is not saying we have evidence that is true. We haven't proven it's true. We just haven't proven it's false. So, you know, try to keep that in your mind. You know, it's just like, you know, if you're thinking about like a court case, if someone is found not guilty, that doesn't mean they're necessarily innocent. That just means that there wasn't enough evidence to say they were guilty. Okay, so it's kind of like that. It's kind of like we're not saying the null hypothesis is true. We're just saying we don't have enough evidence to say it's false. That's what's going on here. All right, why don't you work on these problems and then pause the video and then come back after you get those done. Okay, so let's look at an alternative way to do this. So when I did this last problem, and I got this t-value of negative 1.116, so which correspond to a positive 1.116, I knew this was not going to work. I knew we weren't going to reject the null hypothesis because I knew with that t-value, there was going to be a lot more than 5% up in that upper end. I knew that, you know, that's like just over 1 standard deviation from the mean. You know, just if you kind of remember what the empirical setup was, you know, basically that there's got to be more percent than 5% up there. So this is another way you could do these problems, and you might have already kind of figured it out on your own while you're doing this, is instead of saying, let me figure out the test statistic and figure out what percent or, you know, what p-value, basically what percent is on those extreme ends, let's start off by saying, okay, if I have an alpha of a certain number, what's the cutoff spot? What's the t value that I would stop, you know, from here? It's got to be at least this far away from the mean. It's got to be at least this far away from the mean. That's kind of how this is set up, that there's areas I could set up and say, if you fall in that area, if that t value falls in that area, then it's going to fail. So in the critical regions technique, we'll determine which ones are that failure regions based on the alpha value. If our test statistic falls in that area, we're going to reject the null hypothesis. If it doesn't, we're not going to. Okay, so we're gonna figure out what this t value is, or in the case of a normal distribution, you use the z value. If you knew this population standard deviation, so we're gonna this is our t alpha value, and if you get a t value from your sample, I'll say that's tx, that goes in there, you can say, oh, I can reject it. You know, this is the t value based on the alpha. If I hit a value in there, I can reject it, and if I hit a value over here, I'm not going to reject it. Right? So I'm gonna figure out what that t value has to be for that alpha level. For a two-tailed test, kind of the same idea, except it's going to be based on alpha divided by 2. So if you say 5%, you're looking at setting up the t value based on, you know, 2.5%, because 5% or 2.5 on one end and 2.5 on the other, making that 5% value. Okay, so let's look at, we're going to do number 12 here, and you know, it says go to 28, and then 28 tells you go to 12 and do this. Use an alpha value of 5% to test the claim that the drug has changed the pH either way. So again, my null hypothesis would be that the mean had stayed at 7.4. My alternative would be that the mean didn't stay at 7.4. So we're going to use an alpha level of 5%. And this is a two-tailed test. So what that means is I actually, how do I want to do this? Okay, so since it's a two-tailed test, I'm going to use this, which you'll notice corresponds to a one-tailed test of 2.5, right? And so what I'm going to say is, if my absolute value of my t value is greater than 2.045, that's the corresponding, oh, whoops, I'm looking at the wrong number. I can't see it, that's the problem. Let's see if I can move this out of the way. I don't know if I can. Oh, there we go. Sorry. 4.2 had my, come on. Had my degrees of freedom wrong. Degrees of freedom should be 30, right? So I'm looking at the wrong number. Don't look at this box. This is wrong. I need the box under it. And unfortunately, it's hard to see there, but 2.042. 2.042. Okay. So if I get a value for t that's more than 2.042 when I do the drop the sign off, then I'm going to reject it. I'm going to reject the null hypothesis. Basically, that means I'm farther out to the edge. This is my cutoff. So what's going on here is I'm saying the cutoff areas on these are negative 2.042 and positive 2.042. And if I end up on that end or this end past that point, I can reject the null hypothesis. If I don't, then I need to keep the null hypothesis. Okay. So I'm going to figure out my t value. I don't know why it keeps doing that. T value, just like I did before. I'm going to take my sample mean, 8.1, minus my predicted mean, square root of 31 over, let me move this out of the way. 1.9 looks like what the standard deviation is. And I'm going to figure out what that is. We already did this once, but I'm going to do it again. Minus 7.4, close that up, square root of 31, divide by 1.9, and I get a t-value of 2.051. So I ended up in this end, you know, not really far in that end, but enough. I ended up in that end. I got a value that's more than this. So I need to reject the null hypothesis, which is exactly what we did the first time when we did this problem. We rejected the null hypothesis. So this is just another way, instead of saying, okay, I'm going to get a range of values and, you know, I'm going to compare that range of values to alpha. You could use alpha to just figure out this is the cutoff spot. This is the spot where the t-value, if you go this t-value or more extreme, we're going to reject the null hypothesis. So this is another way of doing this exact same test. It's up to you if you want to use this way. You don't really have to, though I would like you to do it on the homework for this last problem. But you know, in the future going forward, that's up to you. But for 27 and 29, please do it that way. And then going forward, if it was on a test, it would be up to you which technique you wanted to use. All right. Other than that, looks like we're all done. So see you on the next video.